Hi, everyone. Thank you so much for having me. Shout out to Phipps. That was an amazing talk. Before I go into this, I want to let you know we did not coordinate, and that will become apparent in a little bit. So before we get started, how many of you are familiar with React? I just assume that's most of the room, so you all can put your hands up. How many of you are familiar with Redux? Cool, almost the same. How many of you have used TypeScript before the last talk? Okay, good. A lot of you, sweet, because we're going to go into some advanced TypeScript today. So today we are going to talk about building a Typesafe Codesplit React-Redux application, which is a mouthful, but whatever. So my name is Matthew Gersman. As Jared said, I am a senior software engineer at Dropbox. I live in this city. It's my favorite city. It's the best one. So shout out to everyone who came here. You can follow me on Twitter. I spend way too much time there. And these slides are available at slides.slytherin.dev, which we will go into more later. So today we're going to talk about single-page apps. And no, I don't mean applications for people who are single, although those are nice too. Thank you, thank you. I mean like single-page apps, like all your JavaScript is running in the browser apps. I mean create React app. And normally when you go and create one of these, the first thing you type is yarn add Redux, and then you might type yarn add TypeScript. You might add Lodash. You're probably going to start writing a lot of JavaScript. And then you're going to write a whole bunch of CSS. And before you know it, you are serving that your node modules folder is probably the heaviest object in the universe. In fact, shout out to Phipps, you are probably serving on the order of tens of megabytes of JavaScript. And I know that before that last talk, that didn't seem very big, but here are the top 10 fastest internet speeds in the world. So you were wondering why it was slow. It's because, well, we're ranked 10th. The last time I gave this talk was with the same organizers in Norway. Shout out to them. And we have an average speed of 18.7 megabits per second, which means it's going to take 4.3 seconds for that bundle of code to get from the server to the client. And that is not parsing or executing or rendering. That is just shipping bytes over the wire before the user sees anything. So how do we deal with this? Well, guess what? We code split. We just talked about that. So let's frame code splitting in my head, because I might think of it slightly differently, or maybe there's just, it's in my slides. So traditionally, you serve one big synchronous bundle, right? We have this giant bundle in your single-page app. It's probably built by Webpack. You have your vendor dependencies, React, Redux, Lodash, RxJS, whatever you feel like, as long as it's not MooTools, I don't care. Someone thought that was interesting. And it probably has all of the different pages you might need in your application as well. And that's this heavy bundle. And the one good thing we could say is that if you're really, really lucky, you might get a cache hit on repeat visits, but you probably won't anyway. So instead what we want is we want many small, lazy loaded bundles. So our vendor bundle is those core libraries like we discussed, React Redux, and then we'll have our various pages or components, and we'll load them as we need them. And a lot of this sometimes is presented as shiny and new, but it's not at all. How many of you worked with one of these technologies at some point in time? Yeah, so PHP, Rails, Django, like we were serving routes back then. We were serving a vendor bundle back then. It was probably jQuery and underscore, but like it was a vendor bundle. And we also served the page code on each individual page that we cared about. Really what's changed with async code splitting is we've gone from doing this in the server to doing it in the client. So now the client is saying, okay, instead of importing this widget as a synchronous dependency, I'm going to do this async. I'm going to import this thing and await it and then go run my code. And React gives us some pretty great wrappers around this. Those are lazy and suspense. If you're not familiar with them, they look like this. So we have react.lazy, which waits on a promise to be imported. And then suspense, which provides a fallback as we're waiting for that component to load. And these are type safe. So what are we doing here? We're done. Side note, I just have to say this. I really, really miss this man. Here's how much I miss this man. This is a picture from my apartment. I own a bust of Barack Obama. Ask me later how I got it. There is a story behind it. I did not just order it online for no reason. No, we're still here because we need to talk about our data layer. And unfortunately, good tooling doesn't really exist here, especially when it comes to Redux. So I want to just do a brief overview of Redux for everyone in the room, so that way we're all using the same terms and we're all on the same page. So we have our state, which is this key value store. It is a dictionary or a map or an object, however you want to think of it, and it is storing data. It's just raw data. We have our view, which is presumably a React component, which is taking that state and spitting out DOM elements and rendering from it. The view might be emitting actions, which are then dispatched or picked up by the store and passed to the reducer, which is a function that takes an action and the previous state and produces a new state. This should be an overview, not the first time you've learned this. So one more thing, the store itself is the combination of state and the reducer and the ability to dispatch actions, and sometimes people kind of overload state and store. Now you might be thinking, but my application has a ton of reducers. I don't just have this one reducer, and you're right. So in traditional Redux, we'll have the notion of a root reducer, which has multiple slices, and we will slice it up and combine them all, and then when an action comes in, we will pass it to each individual subreducer, and then we will merge it all and create one big state at the end. And just to keep myself out of trouble for the rest of this talk, whenever I say the term namespace or slice, I'm going to use them interchangeably. We can probably find a nuanced difference between them, but we're not going to bother for the next 20 minutes. So let me show you this website I built, slytherin.dev. I'm just going to show you what it does right now. And if I can pull off mirroring my displays like this is going to be a miracle. Cool. This is slytherin.dev. These are famous Slytherins. You might not have known they're Slytherins, but they are. We got Snape. We got me. I'm not famous, but I'm famous to me. We got Lin-Manuel Miranda. We have my girl Taylor Swift. We're going to really focus on Taylor Swift in a little bit. We got Nate Silver. We got Kanye West. We got Aaron Fox, Nikki Holt, and Donovan is actually a Hufflepuff. He snuck onto this website. Or something. I don't know. And you can click, there's a whole bunch of like different things, so we can see things I've tweeted recently. So I was just tweeting random things I don't even know. If we look at GIFs featuring Severus Snape, it pulls up all of these GIFs. How many of you remember Potter Puppet Pals? Yeah, cool. That's just, I went with Puppet Snape for the query as opposed to Snape because it was way more interesting. And that's really all this website does. It's not that big a deal. It just like loads different types of data for different people. Really, I just needed to come up with a bunch of different APIs that require different reducers so that we could talk about code splitting them. That's really the whole point of that. I love smoked salmon. That's why I went to Norway. Cool. So that was slytherin.dev, and before we start diving into some code, I want to leave you with I want to introduce you to two advanced types. The first one we're going to be using a lot of is called a discriminated union. And what this is it says the type of store keys is exactly one of these string literals. So it's, in this case, the string literal is a type, so it's Giphy or movies or podcasts, and it is one of those many types. In this case, we have 6 in our application. The next one I want you to know about is generics. Now, generics are a way for TypeScript to infer at compile time what the type of an argument is. So in this case, we have K. This is all kind of the syntax around generic. And this function is just automatically going to infer what K is and return the value as that type and maintain type safety as you're calling it. So in a naive implementation of slytherin.dev, which I promise when we get to the end you're not going to think is naive, we have our root reducer, which has our 6 different namespaces: GIFs, RSS, movies, Twitter, podcasts, YouTube. I really only ever use GIFs and Twitter, but whatever. They're there. Our state is also like that, and then all of our actions and all of our selectors are available at all times. Our store shape looks like this. So this is a TypeScript type. So the keys are the namespace keys. So in this case, we have Giphy, and then we have Giphy namespace, which is an object. If you go up here, you can see that's where I'm declaring the string, and then Giphy namespace is a mapping of Slytherin ID, which is just user ID, but it's way better because I love Slytherin, and it maps to a Giphy image. How many Slytherins are here? I love how just like millennials like casually know what their Hogwarts house is. How many people in this room know their Hogwarts house? Yeah, see, look at that. Everyone, it doesn't matter how big a fan you are. We're also rounding up every action in our application. So this is a discriminated union of every possible action within our application. You're going to see why we do this in a little bit. In our root reducer, which is actually more complex, but for here I'm just simplifying it, we are slicing up the individual reducers, so in this case Giphy, and we are narrowing into it and passing that slice of the state along with whatever action comes in, which is one of any action that we know about in our application. For our selector layer, it's pretty straightforward. We just select something from state, and we're selecting a value off of it, and it's type safe. Hopefully that would be type safe. And we get some pretty cool immediate wins from the way this has been typed. So we type our dispatch function so that if a user goes to dispatch an action, and it's an action that we know about in our application, it's going to work. If they go to dispatch an action that we don't know how to handle, it's just going to yell at them, probably in their editor, if they're using the right plugins. If not, it'll yell at them in CI, so that's good enough. Same thing for selectors, because we're just selecting values off of objects. This is kind of very much table stakes for TypeScript. We select Giphy off of the state, it works. We try to select an invalid thing off of the state, it yells at us. Then with our actions, we have this all actions. You've probably seen a switch statement like this, where we're switching all this, where we're switching. What's super cool is TypeScript knows, because we've done this discriminated union, and there is exactly one action with this string, it's smart enough to figure out that the payload of that action must look like this. So inside of our function, we know exactly what type this payload is, and if we try to get something invalid off of it, it's going to break. So it's really smart that way. That was our naive implementation. When I say naive, I mean no code splitting, which is what we came here to talk about. So you may have thought actions are probably easy to code split. They actually are easy to code split because they're just objects or functions that create objects or thunks or whatever, but you can usually tuck them off in some part of your application and forget they're there. Selectors are even easier to code split. They're just functions that take some data and then return, some value derived from it. Reducers are really hard to code split. Why are reducers so hard to code split? Well, we need the root reducer at store creation. The very first argument to create store is the root reducer, and the root reducer is made up of every possible reducer this application could ever need. So now I'm going to tell you a little bit about Dropbox scale, because there's a whole lot of complexity here that really doesn't make sense without the context it was built in. And that's just something I hope you know in general, that a lot of the time we build complexity because we have to, not because we wanted this to be complex for no reason. So this was built for Dropbox, and the first thing you need to know is it was written in 2017, and we had an ongoing performance initiative. So we were trying to improve TTI across the board, and we were running React 15 because that was what was out then. So this was very much built in that world. We had 200 some odd engineers working on the same code base, 25 namespaces at the time, so 25 different reducers. Any given page might need a permutation of 5 to 10 of them. And just because we want to make things more difficult, we have 4 offices and 3 time zones. And this code has to run on every single page because it's our core state management code. This is what manages Redux. So we're either going to have a million stores or we're going to run one set of code on one page, or on every page. But we can't guarantee that a single reducer is never expensive. Frankly, nor should we, right? The RSS team might need some crazy XML parser that's really big. The GIFs team might want to import all of Lodash, and while I don't recommend that, that's not my problem, and that shouldn't be a limit based on the implementation of the architecture. That should be a limit based on the fact that Lodash is 25K. So we've got to figure out how to code split the reducer. And that's where we kind of come back to Slytherin.dev, and we start talking about my girl Taylor Swift. How many of you love the new album Lover, by the way? I'm on the order of 100 listens, but all these screenshots were taken 6 months ago, so it wasn't out yet, so forgive me. So we navigate to Slytherin.dev, and we see Taylor, and we have our root reducer, which is empty, and we have state, which is empty. We navigate to see her tweets. She was talking about something. Hey, she was talking at the Netflix marketing team, Ryan. And we fill in our root reducer and our state with Twitter. Later, we click the GIFs page, and we see these great Taylor Swift GIFs where she is demonstrating that she is a Slytherin. That is some awesome side-eye, and we have loaded in that reducer and that state. Let's see how this works live, shall we? So let me mirror again, or unmirror, yeah, whatever. Cool. And this is my unpreloaded version of Slytherin.dev. So I'm going to open up the Redux DevTools for you. I'm also going to throttle my connection to fast 3G just so you can see things happening. So I click on Twitter for Taylor Swift. You can see we're loading the reducer, and then we're hitting the API. We're doing one, then the other. And you can see here we've made that request. And in Redux, our state has just the Twitter state in it. If I go back and I click on GIFs for Taylor Swift, images take a long time to load because it's slow 3G. They're going to pop in. But you can see we added that namespace in the state, and we've also started pulling in this data. And we could do this with anyone. Now, for example, if I went to GIFs of Severus Snape again, you can see we don't need to load the reducer because the page code is already loaded, but GIFs take a really long time to load on a slow network, so I'm going to go online, and look at that, all those puppet Snapes. Wonderful. Cool. So that's this thing working live. Now let's kind of dive into the actual source code. Well, if you've ever given a talk, the fact that I managed to mirror, unmirror, and mirror is a small miracle, but I'm really excited about that. So what do we want to optimize for in this application? Well, we want to optimize for soundness. What do I mean by soundness? Well, we want it to work perfectly or completely break. We want absolutely nothing in between. So the kind of things we want to avoid are silent errors, or it works on my machine, or some bug around render order where they loaded this page first and then they went to this other page and it worked, but in reverse it doesn't work. So we want it to be sound. We want it to always behave deterministically. So how do we enforce soundness? Well, we can do it in two places. We can do it at compile time, which is the TypeScript layer, or we can do it at runtime when the code is actually executing in the browser. The thing is, if we can't guarantee something at compile time, we better do a really, really good job of guaranteeing it at runtime. And as far as I'm aware, the best way to do that is just to fail hard and fast. So that way it fails in your dev environment, and you just know immediately that something's wrong, as opposed to some race condition that only comes up at scale. And on top of all of this, we also want to have a decent developer experience. We don't want them to be worried about how all this code splitting works all the time. So looking at app.tsx, our main entry point for Slytherin.dev, you can see I'm just React.lazy loading all of these various pages. And I'm using Suspense the same way you would regularly. And if we dive into our GIFs page, you can see I've added this thing called the Codesplit provider. How many of you have worked with React-Redux, the library? Cool. So this is going to be very similar to React-Redux for reasons. So the Codesplit provider, which is very similar to a React-Redux provider, takes a mapping of namespaces to reducers that it cares about. Below that, map state to props and map dispatch to props work exactly how you would expect. And this is a bound action creator, which works exactly how you would expect, because that's what we optimize for. So this is a similar cognitive overhead to lazy and suspense in that they need to know to use the tool, but they don't need to know too much about how the tool works, so that's nice. So how does this particular tool work? Well, we have our provider.txt, TSX, not a text file, which calls a function called getStore and register reducers. And then it's using React-Redux under the hood, which is why this looks so much like traditional React-Redux, because it is. And this function enforces a singleton pattern. So what we've done is we have scoped some state internally to the module, which is the store, and we are saying we are only going to have one instance of our Redux store. If it's there, great, we'll register anything we need. If it's not there, then we'll just make it and then put the reducers there. When we go to register reducers, we do some sanitization that I'm going to skip. And then we're also storing a map of every reducer in our application as well. To do the actual swap, we use combine reducers, which is exported from core Redux, and then we use replace reducer, which is also part of the store, and that is a function that allows us to wholesale swap out the reducer in place and keep the state where it is. So that way we can use this new data, and presumably we're only adding reducers, we never remove them. But our GIFs team doesn't need to know about that. All they need to know about is this code split provider. So what about typing this, right? Well, we want very different things at runtime and at compile time. At runtime, we want to have this root reducer where modules are getting swapped in and out, or really just in, at any given point in time in any order. But at compile time, we want to know about anything that can ever happen in our application. And we can pull that off with TypeScript because it's really powerful. So to do that, we make this central types.ts file, and we have our same full store that we had in the naive implementation. But now we're exporting this thing called store shape, which is what we actually call it, and it is a partial of full store. A partial in TypeScript is just saying every key is either there or it's not, but if the key is there, all the guarantees of that object are true underneath it. So all the guarantees of the Giphy namespace are true. Our selector layer is our single point of failure. So this is really where we can optimize for to check if some reducer or namespace hasn't been registered when we need to select the code. So internally, we might be calling get gifs for user ID. We're going to call this function called getState@namespace. And in my opinion, this is some of the coolest TypeScript I've ever gotten to write, so we're going to walk through it. So getState@namespace takes state and key, which is the actual state, and then the top level key that it cares about. It's going to then split full store. It's going to split the slice into full store, which is the actual namespace, or undefined. If it's not there, we're going to throw. If it is there, we're going to return. And that throw is very much the fail in dev mode. Now, there's some kind of crazy stuff going on here with generics, and we're going to go into that. So the first bit I want to cover is store shape. Just as a refresher, that is the partial of full store, and full store is the whole store. So anytime you see full store, it means we can trust the key is there. Anytime you see store shape, it means we need to go check to see if the key is there. The next bit is K. This is our first generic. K extends namespace key. So what we're doing is we're putting a constraint on this generic and saying it must extend this thing called namespace key. So what's namespace key? Well, namespace key is key of the entire store shape. So that is a discriminated union, if you remember from the beginning, of these 6 types. So we know that K is going to be exactly one of these 6 strings, or it's going to yell at us at compile time. So it's going to be Giphy or movies or RSS or what have you. We can then index on a type in kind of that typings layer and do full store of K to produce the namespace type. So now we can actually use these types by referencing an index on another type. And then this works the way I described before. We split it into 2 types, so we know the falsy case and the it's there case. Throw if it's broken, return if it works. Cool. Last bit in this code split application is how actions work. Now, we can round up all of our actions using type-only imports. And the advantage of this is all these imports are just types, which means once TypeScript's done compiling, it's going to throw all these out, and there won't be any more dependencies once Webpack actually picks up our application and does all the dependency management. And there's a clear trade-off here. We are losing some modularization, right? Traditionally with Redux, you're just dispatching actions. It's based on a pattern called event sourcing, and you really don't need to worry about who's going to pick up the action. You just know that you're firing it off. But as I mentioned, we had 25 different namespaces, which is almost a proxy for 25 teams in 3 time zones. And we need a way to coordinate all these actions. And how many teams are going to make an action called fetch or success or get or like get file or write file or just, these very basic things that they might just forget to namespace? How likely is a collision without forcing this upon a large number of developers? Eventually, we're just scaling for like our code base and number of engineers. So we've got to coordinate to prevent conflicts, and I think it's way better to do it in the TypeScript layer than some document somewhere. So types.ts looks almost exactly the same in this solution. We have typed dispatch, so we can only dispatch actions we know about. In the real code for this website, I have added a Slytherin standard action for my own amusement, mostly because I needed a user ID, but also because the type is a discriminated union of every string we know about, and that gives us those same payload guarantees we had on the other ones. So to do that, we round up all of the types from all of our individual action modules. Inside of the GIFs module, we will round up all the GIF actions and then just export them as a union of all the actions we know about. These are the various actions. These are some of the enums you might see. And then our reducer has those same guarantees, where we switch off of fetch success, and as a result, we know the exact shape of the payload because of that string in our entire application, no matter how many actions or how many selectors we have. So that's how all this worked under the hood. Let's kind of return to our goals for a second. Our goals were soundness and developer experience. And we accomplished that with 3 things. The first one is the developer needs to know about the code split provider, which guarantees that namespaces or reducers are registered. They need to know about getStateAtNamespace, which is this kind of core selector. And they need to know about types.ts, which is this typings file. And I think that's pretty good as far as cognitive overhead goes. Now, I want to call out the future of this code because, like I said, this was written in 2017 in the React 15 days. And guess what? Just like everything else, this code is going to die. I don't know when, but it will. The React ecosystem is constantly changing. We have Apollo. I didn't even mention hooks today. And there's just constantly new things. The real takeaway I'd like you to have is that there is no silver bullet for global state. This is just, in my opinion, one very interesting implementation based on the constraints we had at the time. So I have a whole blog post about this that you can pull up. It's easier to find on the slides, which is slides.slytherin.dev, and some references. Thank you so much.